Thank you very much. I'd like to start by thanking the organizing committee for organizing this for me and all the technical help. I feel bad about all the trouble that I've put you to, but it's very much appreciated. I really thought that had some setbacks, and anyways, this is definitely very good for me. Thank you very much. So the title of my talk, as you can see, I hope, is the difference calculus for functors on presheaves. So what I want to do is to take Newton's difference calculus and generalize it to functors from sets to sets. So his delta operator takes a real valued function and it gives a new one, delta f, which is f of x plus 1 minus f of x. And this is a discrete version of the derivative, and this is very useful in practice. There are all sorts of versions of this. This is the simplest one. And so I want to take this and do the same thing for functors now from sets to sets. And so this is part of the general project of trying to understand the structure of functors from sets to sets. So we know, for example, for the work on polynomial functors, and I give some references here. There's many people who worked on this, Koch and Spivak, and many others. There's a beautiful theory of polynomial functors, and before this there were the analytic functors of Joyal, also beautiful theory there. So inside of just endo-functors of sets, there are all sorts of interesting things going on. And so this is a contribution to trying to understand what endo-functors of sets are. And then sort of encouraged by these multivariable analytic functors, for example, in the paper of Fiore and company, I want to generalize this then to the multivariable case. And in the back of my mind, there are always differential structures, Cartesian differential categories or tangent categories and so on. This is sort of part of that. And it's related to many things. I just mentioned two. So the Cartesian difference categories of Alvarez, Picado, and JS. I don't really understand the relationship, but certainly looks like there's something there. And it's also maybe a discrete version of the Goodwillie calculus, or maybe a non-additive version. And so there's this paper here by Bauer and company, which talks about that. So the general idea then is this: is to take a functor from sets to sets and look at what happens to it when you perturb the input. So you change the input a little bit. So the smallest I can do is add 1 to it, and then see what extra things I get. So here are two simple examples. So the first one is f of x equals x cubed. Then f of x plus 1. So is there an echo there? Yes? Yes, maybe. No? No, okay. So I take a functor that takes x to x cubed. Then f of x plus 1 has 8 kinds of elements, so they're triples. Either maybe all of the entries come from x, so x1, x2, x3, or maybe 2 of them come from x and 1 comes from the unique element of 1, which I'm calling star. And there's 3 places to put that star. And then maybe there's just one that comes from X, and then there are 2 stars, and there's 3 types of those, or maybe 3 stars. And so what I get then is that this delta f of x is 3x squared plus 3x plus 1. So this is something that you can easily calculate algebraically for real valued functions, but this here is a bijective proof of this. Another example is the covariant power set functor. And so if we look at subsets of x plus 1, there are 2 kinds. Either the star belongs to it or it doesn't belong to it. Those that belong to it are in bijection with subsets of x. They're A union the star. And those that belong to x, we remove those, and so what we get then is that delta f of x is 2 to the x again. Another thing that you could easily calculate algebraically, but again, this is a bijective proof. So, of course, this f of x plus 1 minus f of x, this is set difference. And of course, it's not functorial in general, and this is probably why you rarely see this in categorical contexts. But in fact, it's functorial for a large class of functors, the top functors. So in this paper in 2002, where Nimanis studied top functors with regard to theoretical computer science, and so he defined a top functor to be one that preserves inverse images, by which he meant preserves pullbacks of monos along an arbitrary f. And a natural transformation is taught if the naturality squares corresponding to monos are pullbacks as well. I should mention that these appeared earlier in work by Turnkova in the late 60s, where she was studying precisely the structure of endofunctors of sets. She had many conditions, and this was one of them, but she didn't single it out, whereas Ernie here singled this out as being the thing that he needed, and this is what we need as well. So you can compose top functors, and you can compose natural transformations in various ways, and you get a sub-2 category top of cat. Okay, so the objects are categories with inverse images, and the 1 cells are top functors, and the 2 cells are natural transformations. These are exactly, well, this is what we need for our calculus, but let me just, first of all, try and explain why there's a lot of these functors, okay? So, first of all, they're closed under limits. So this is just a question of limits commuting with limits, but you have to be a little bit careful where you're taking these limits. So, first of all, if you take them in cat, so you take a limit in just a diagram in cat set, whose objects are top functors, but the transition maps are just arbitrary natural transformations, then you get a top functor back again. And on the other hand, if you restrict the natural transformations to being top, then you don't get all limits, you get non-empty connected limits. But they're limits now in top, so that they're better. And so in particular products, they're not connected, but of course the transition maps are top, but a product of top functors is top, but the projections are not. Or even the terminal object is top, but it's not a terminal object in top. Okay, so this is the story for limits. This will give you lots of different top functors. Of course, co-limits don't commute with limits, but in set we know, for example, that filtered co-limits commute with finite limits. So a filtered co-limit of top functors would be top, and so we can characterize those co-limits that commute with inverse images in set. And there are these that the indexing category satisfies the following condition. Any span in there can be completed to a commutative square. So I call these confluent co-limits. This is easy to prove, but I haven't seen it anywhere in the literature. Maybe people never needed it. But anyways, this is I think is a nice result. So for example, filtered colimits, as I just mentioned, but coproducts, of course, are confluent, but also important for us are quotients by group actions, or maybe a colimit over a groupoid. All of these are easily seen to be confluent. And so now the story for limits is that the story for colimits is that confluent colimits in cat set of tot functors are again tot. And if, on the other hand, we take diagrams in tot, then all colimits exist and they're limits in tot. Okay, so that's the story for colimits. A couple of examples here. Polynomial functors are tot. So a polynomial functor is a functor which is a sum of exponentials, and the exponentials are Hom functors. And Hom functors preserve all limits, and then we take a sum of those, and so those are tot. So the polynomial functors are tot. Analytic functors are also tot. So analytic functors are sort of similar, but now we're modding out by the action of the symmetric group, and those are also tot. And Ernie Manes said that collection monads are finitary tot monads. So I'm not sure if he was taking that as a definition, or a characterization. Collection monads existed before that paper, so I suppose that it was a characterization of collection monads. So that's why he was interested in these tot things. So now we come to the main definition of at least the first part of the paper. If f is tot, then the difference is functorial. In fact, it's better than that. It's a tot subfunctor of the shifted f. A tot transformation restricts to the difference functors. Okay, so and furthermore, this delta f is functorial in f, and so we get a functor from tot set into itself. And this is the difference operator, and this is what I want to study here. So here's some trivial examples. If you take a constant functor, then of course f of x plus 1 and f of x are the same. You subtract, you get the empty set. And if you take the identity functor, which I'm writing here as x, then delta of x is 1, which is easy to see as well. Now, in fact, delta preserves colimits, but they're colimits for diagrams in tot. Okay, and so you need this, even though the colimits exist for diagrams in cat. For diagrams in tot, you need it because you need to make this delta gamma I functorial, and so you need the transition maps restrict. Okay, but in any case, delta preserves these colimits, and so this is a generalization of the addition formula for delta. So delta of f plus g is delta f plus delta g, and also it generalizes delta of a constant times f, because the constant times f is the coproduct of copies of f. Now, products in some limits are more interesting. So delta of a product, we don't have exactly the Leibniz rule, we have a modification of it. So delta of the product is delta of the first times the second, plus the first times delta of the second, plus this extra term, delta f plus times delta g. Okay, so this is the same for functions of real variables. This is a kind of Leibniz rule for delta. This is a purely set theoretical thing here. I mean, it's easy to prove for functions of real variables, but here it's not hard. This is purely set theoretical, and so you can actually just do it for arbitrary products. You take a bunch of f's, but not all of them, and their product, and then you take delta of the other ones and their product, and you multiply those together, and you sum all of this over proper subsets of them. Okay, so that's delta of the product. It's the same proof. Okay, I don't know if it's useful in this generality, but there it is. And as far as the non-empty connected limits are concerned, they're preserved by delta. So that's the story for that. Now, in general, there's no useful chain rule for functions of real variables, as far as I can tell. But now, because we're in CAP, we have more wiggle room, and so the things that we might have expected to be equal are not equal, but there's a comparison between them. Okay. In fact, they're not equal even if you take f and g just to be squaring, x squared. You don't get equality here. Okay, so, but you get this comparison between the delta g composed with f times delta f into delta g tensor, g composed with f. Okay, it's monic, it's natural in f and g, and it's associative in the way that you might expect. You want to take a composite of three functors and take the difference, and you want to compare that with the difference of each of the individual functors suitably evaluated. And so you have two different ways of comparing it, and they're equal, and then it's also unitary. So this is why I call it a lax chain rule. It's just that the thing that you want to be an iso is just a morphism, there's just a comparison. But we can actually make it into something lax. And here, we can look at tangent structure. So I haven't gone into this in any detail, but I define the tangent space of set to be set cross set. So this is just an analogy with the fact that the tangent space of the reals is the reals cross reals. But I mean, it's the thing that makes this work. So now we can extend any tot f to the tangent space, and by this formula here, t of x y is f of x, and delta f of x cross y. So you notice that it's linear in the y here, and what you get then is actually a lax normal monoidal functor. So tot set is monoidal category under composition, as well as for set cross set, and so you get the monoidal functor. So for example, tot monads on set would go to tot monads on set cross set. So here is an example. I can calculate actually the difference for polynomials. So if we have a polynomial functor, then its difference is again polynomial. And we can calculate the difference. It's the sum of the x to the s's taken over all the proper subsets s of all of the ai's. So for example, just the representable functor, or power x to the a, is the coproduct of representables x to the s for proper subsets of s. And if a is a finite cardinal, then we can group like terms together and get this formula here, which and this is n choose k, the binomial coefficient. So this is a generalization of the example I gave with x cubed. Now, I want to sort of, there are more things to do here, and I don't have time to go into everything, and so I want to go on now to the multivariable functors, which in fact was in the title of my talk. I want to extend the difference calculus now to functors between presheaves categories, sets to the a, sets to the b. And so such a functor I'm thinking of as a b family of functors in a variables. So I want to take the partial difference with respect to an object a in a. And so for that, I take an object and sets to the a, and I perturb it a little bit by adding in a single element of type A freely. So that is simply just adding on the Hom functor, Hom A blank. And so we want to define now the partial difference of f at phi is going to be f of phi plus the Hom A, minus f of phi. And now the one variable theory carries over with some modifications. The modifications involve profunctors. And so, excuse me, for me, a profunctor from A to B is a functor from A opposite cross B to sets. So this is not the majority definition, but anyways, okay, this is what I'm taking, and then the morphism of profunctors natural transformation, and often the profunctors are billed as a categorified version of relations, which is true, but it can also think of it as a matrix of sets, so it's a categorified version of matrices. Now, composition is matrix multiplication, which is given by Cohen, and identities are the Hom functors. So a profunctor from one to A is functored from 1 up across A into sets, and I want to identify that with the presheaves. So I want to identify presheaves with profunctors from 1, and now I can compose this phi with a profunctor P, and I get a new profunctor, P tensor phi, in sets to the B. And so we get a functor, then P tensor blank, going from set A to set to the B, and this is it's co-continuous. So you can think of this as a linear or a two-linear functor. Now we just calculated its partial difference, delta A of P tensor blank at phi is this is P tensor phi plus Hom A minus P tensor phi, and because P tensor blank preserves coproducts, we can break it down as in the second line here. Take away the P tensor phi, and we get P tensor Hom A, and then the identity relation for A says that this is just P evaluated at A. So this is, we're thinking that tension by P is linear, and what we get is a constant. It's a constant when it's independent of phi. So it takes any functor phi here to this functor P A blank. Okay, so now, however, this P tensor blank, it's a very nice functor, but it's not top. Doesn't even preserve monos. Top functors preserve monos, and so it doesn't preserve Kovacs of monos, and it's not top. So I want to modify the definition of top, but top is pretty well established. In any case, I need it. So I take the term tense, which sort of sounds like top, and it's more or less a synonym of top, and it also sort of evokes tensors. And so I say that F is tense if it preserves complemented subobjects and their Kovacs. Okay, so I simply change the definition of top to deal with complemented subobjects. In presheaf categories, complemented subobjects work very well. So natural transformation is tense if the naturality squares corresponding to complemented subobjects are Kovacs. So if F preserves binary coproducts, for example, it's tense. And so P tensor blank is tense. So that's good. We can now get off the ground with this. You can compose tense functors and tense natural transformations just like for top. So we get now a two category. It's a sub-two category of cat consisting of presheaf categories, tense functors, and tense natural transformations. Now, this is a review now of the limits and co-limits story from before. The same thing applies. Suppose we have a diagram in cat such that all of the values are tense functors for every I. Then its limit is tense. And if I is confluent, its co-limit is tense. So that's the story for diagrams where the natural transformations, where the transition maps are just natural transformations. And on the other hand, if you require the transition maps to be tense, then it creates just non-empty connected limits, but all co-limits. So it's the same story as before. I just rewrote it a bit differently. Now, we can define the partial difference. So the partial difference is what I said it was going to be, f of x plus Hom minus f of phi plus Hom A minus f of phi. We get a tense subfunctor of f shifted by this Hom functor. And this is functorial in f. And so we get now a functor that goes from tense set to the A into set to the B into itself. this is, we call this the partial difference of f with respect to a. And again, if you take a constant functor, you get 0, okay, it's trivial. And my calculation from before says that if you take now sort of a linear functor, p tensor blank, then you get just p back at a. So, delta A preserves colimits and non-empty connected limits. Okay, it's the same as before, and so in particular, you have the addition formula and also multiplying by a constant, and you have this generalized product rule, and the special case then is simply the same as for top functors. Okay, so this is simply the same. Okay. Now, this delta is functorial in everything. Okay, so you start off with the tens functor, then delta AF of phi for a fixed phi is contravariantly functorial in A. So you get a functor, delta, without the A now, delta F phi, going from A opposite into sets to the B. So a functor from A opposite into sets to the B is a profunctor from A to B. So this is the kind of discrete Jacobian of F at B. So I'm thinking, right, a profunctor is a matrix, and so for each phi we get this matrix here. It's also functorial in phi. And so delta F now gives you a functor from sets to the A into sets to the A opposite cross B, or prof AB if you like. This is also a tens functor. And it's also functorial in F, and so we get now the Jacobian functor. Delta goes from tens AB, set to the A, set to the B, into tens set to the A, set to the A opposite cross B. Okay, so this is all the functorial properties of this delta. Now, we can sort of formulate this a little bit differently as a differential operator, going from set to the A, cross set to the A to set to the B. It takes phi and psi, and it gives you delta F phi tensor psi. This is co-continuous in the second variable, as you can see. And you can also get sort of a tangent space version of it, where you lift F to set to the A, cross set to the A, to set to the B, cross set to the B. So again, now I'm supposing that the tangent space of set to the A is set to the A, cross set to the A. And it's simply the same formula as before. You take F of phi, and you get delta F of phi tensor psi. So it's co-continuous in the second variable. It's linear, if you like, in the second variable. And we have also lax chain rule. And so for tens functors F and G, and phi in set to the A, we have this canonical comparison. So actually saying that delta F phi is a profunctor maybe doesn't mean that much. Maybe it's just an element of a presheaves category. But here we see that we're using profunctor composition in this comparison. So this is sort of evidence that really we should be thinking of it as a profunctor rather than just as a presheaves. So it's the same formula now. We can compare delta of a composite with delta of each of them suitably evaluated. It's natural in phi, it's natural in F and G, it's associative just like before, and it's normal. I don't think it's monic as it was in the one variable case. I don't have an actual example. And so we get then a lax normal functor going from this bicategory tens to itself, which takes a functor, takes an object set to the A to set to the A cross set to the A, and it takes this F to TFF. Okay, so this is white flags, if you like. Now, it wouldn't really be any good if it didn't apply to the multivariable analytic functors. These are really very nice functors. Just after Fiore and company, I just quickly review how they defined these multivariable analytic functors. First of all, you construct a three-symmetric monoidal category generated by A. Subjects are finite sequences of objects of A, and morphisms are finite sequences of morphisms, but controlled by bijection from n to n. So m has to be equal to n for there to be morphism there. And they defined a symmetric sequence, or multivariable species, if you like, to be a profunctor from bang A into B. And then this defines a multivariable analytic functor, going from set to the A to set to the B, by count extension. Well, it's a little bit more complicated than that, but what it comes down to is you take the co-end over this bang A of P evaluated at some sequence of A's and B now, and cross P of A1 cross P of AN. Okay, so these are like the powers of X in a multivariable analytic function. Okay. And so P tilde is tense, and delta of P tilde is an analytic functor again. Okay, and we can actually calculate the species corresponding to delta of P tilde. So it's a little bit complicated. So given a symmetric sequence, an AB symmetric sequence, we get another A opposite cross B symmetric sequence Q, defined as follows. Q of A1 to AN, now at A and B, is the co-product of P with the A1 to ANs, and then we put in KAs, at least one of them, and then at B we evaluate P at B, and we mod out by the action of the symmetric group on those A's that we just added in. Okay, so there are KAs in this summand, in the case summand, and SK acts on those, and then we mod out by those. So that's what the Q is. So when A and B are 1, bang A is just this category of finite cardinals and bijections, and then we recover the original definition of species, an analytic functor, and so now this Q, the new species, is, we can just write it like this, it's the sum from k equals 1 to infinity of Pn plus k, but then we mod out by the symmetric group on k. So a Q structure on n is a positive integer, and then an equivalence class of P structures on n plus k, and two structures are equivalent if there's a permutation of n plus k that fixes the first n elements and transforms one of the structures into the other. So that's what this is. So people who know about the derivatives of analytic functors, you'll see that that corresponds to just the case k equals 1 here. Now, here's something a bit more speculative. How should we categorify the exponential functor a to the x? Okay, so I'd like to go to the categorical version. So this is one variable now. We're going back to the one variable case. So I just want to give this as a different example from the others. Polynomials are special cases of analytic functors. So basically just have one example as analytic functors. Okay, so this is a different kind of example. These functors are not, don't have rank. Well, I haven't told you what the functors are yet. But so what the a to the x is only defined for positive a. And so how are we going to
I mean, all sets are sort of positive, so how should we, what should we take to replace positive A? So we have one example, is covariant power set functor, and we can sort of bootstrap that and take products of those, or maybe generalize it, replace 2 by 3, get a similar thing, so on. So what makes all of those work is that 2 or 3 are soup lattices. So here, this is a bit of a stretch. I want to replace the positive sets, positive elements, by simply soup lattices. So we can take now L to the X and make this into a covariant functor from set to set by time extension. So if we have a functor from X to Y and an element of L to the X, then f of f at phi, at Y, is simply the soup of the phi of x's over the inverse image of Y. So we take all inverse images. So this generalizes the direct image functor for the covariant power set. And so in any case, whether you think that a positive set should be replaced by soup lattices or not, this gives, anyways, nice Todd functor from set to set. And its difference then is just a sum of copies of L of x, where the indexing set for the sum is this L star, which is L minus bottom. Okay. So that's what this is. Now, for example, if you take 3 to the x, the 3, I'm thinking now 3 is a totally ordered set, finite totally ordered set, so it's a soup lattice. And its difference then is 2 times 3 to the x, something that you could also calculate algebraically very easy. Now, I'd like to define Dirichlet functors as sums of these, but I don't like this definition. I don't think it's right. And the reason is that this sum doesn't determine the LIs. So the functor itself doesn't determine the LIs. And the reason for that is that L to the x is not connected. So there are components there, they can sort of float around if you like. So, for example, if you take the nth ordinal, so 1 less than 2 less than n, this is a soup lattice. And now, if you take any increasing sequence of n's, and you take the sum of these ni's to the x, it's going to be isomorphic to any other such sum. So, for example, the sum over all n's. As I said, the reason is these components in here can float around. So, the set of components of L to the x is L. And you can decompose this. You decompose L to the x into its components. So each component the component corresponding to L is a set of functors from x into L whose soup is L. So this leads me to define the normalized exponential, for lack of a better name, and for lack of a better notation, I denoted L to the brackets x. And it's simply the set of all functions from x into L whose soup is the top element. And now L to the x is the coproduct of this L slash L, little l, to the x. So L slash little l is just the common category, which is the downset of L, if you like. It's the set of L prime that are less than or equal to L. And these guys are also taught. And the difference now is not as nice as before. It's a sum of these slice lattices to the x, taken over pairs L prime, for L prime not bottom, but whose join is the top. This is a funny condition, but if you think of the dual one, we'll just say that L and L prime are disjoint, right? So it's sort of co-disjoint, if you like. So this is the formula for the difference of the L to the x. and if T is jointly reducible, for example, which is a concept from lattice theory, meaning that you can't write T as the joint of two smaller guys, then delta L to the x is isomorphic to L star cross L to the x, L to the brackets x, plus then the sum of these splice guys over all splices except for the top one. Okay. So this is the difference for L to the x. And now I want to define Dirichlet functors, covariant Dirichlet functors. So there are already some definitions of Dirichlet functors in the literature. This is different from them. So if I take two families of soup lattices, such that the functors that they define by taking the sum to the sum of the normalized powers, if these are isomorphic, then there's a bijection in the indexing sets, and there's an isomorphism between the lattices. So the bijection on the indexing sets is easy because the indexing sets these L to the brackets x are connected so that I is just a set of components of these functors here. Okay, so it's a little bit tricky to prove that L that you get an isomorphism of lattices here. And so I define now a Dirichlet functor to be a functor of this form here for Li, here a family of soup lattices. Now, the difference of Dirichlet functors is again Dirichlet. First of all, let me just mention they're taught and they're closed under products and coproducts. Coproducts, it's obvious, that's from the definition, and for products it's easy because L to the brackets x cross M to the brackets x is L cross M to the brackets x, okay, and so you just did. But infinite products as well. And then, if f of x is this Dirichlet functor, then so is delta f of x. And here I can actually calculate what the difference is. It's the sum of these splice LIs to the bracket x, and the sum is indexed by all L's, and then L and L prime such that L join L prime is the top, and L prime is not the bottom. So, there are many things that I haven't touched on, and there are many things that I haven't explored yet. I think there are many things to do. One of the things I just mentioned quickly is that for top functors, and probably for tense ones as well, although I haven't worked it out, there's a summation formula similar to Taylor series. I haven't talked about this at all here for lack of time, but it involves generalizing species to what I call soft species, where instead of having finite cardinals and bijections, have finite cardinals and surjections, and then this summation comes out as a left adjoint. So this is nice. This is very much related to a paper by Zawil and Zavodowski on what they call semi-analytic functors. They're more or less the same thing. And so here are some references, and that's all I have to say for today. There's some time left over for questions, I guess.
For your interesting talk. Now we are going to have the question session. And so this is going as follows. I ask everyone who wants to ask a question to come here and to speak here, okay?
speak into that one?
Here, you have no, it's okay here. It's
Okay. Hi Bob, this is Tom Leinster. Thank you very much for your talk.
Hi, Tom.
When Giancarlo Rota introduced his theory of Mobius inversion for posets in the 60s, he said that he was generalizing two classical theories. And one of them was Mobius inversion for natural numbers, and the other one was the difference calculus. Now, Mobius inversion for posets has been generalized to Mobius inversion for categories in a couple of compatible ways. So the question is, do you envisage some connection between your functorial difference calculus and categorical Mobius inversion?
I haven't. There's an echo, yes? No?
We don't hear it.
No, oh, good. So I haven't actually looked at that. It sounds very interesting. And as I said, there are many things to look at, but I will write this down here in Mobius inversion and look into that. It sounds like it probably has. I mean, there are relations to everything. It's just that you have to work them out, and they're often not exactly what you would think they are. But yes, it's an interesting question. I will look at it. Thanks.
Thank you. Thanks.
Any questions?
I will mute you when you stop speaking, okay?
Hi Bob, it's Richard
Hi.
here. How are you going?
Yes,
So my question is as follows. I wonder if you have thought about reduced power functors.
Yes, I have, and indeed they're in the paper, which I'm going to put on archive soon. I didn't talk about them today, lack of time, but indeed I have. They give you top functors, and you can calculate their difference, and so on. This is a nice class of functors, which in some sense, I mean, they're not polynomial functors and they're not analytic functors, but they're sort of similar. And so I have looked at that, and there are formulas for the difference of the symmetric, of the reduced powers. Yes, yes, yeah.
Great, thank you very much. So
Thank you.
maybe just one extra comment. So the category of taught functors is a presheaf category, and the representables are the reduced power functors. So
Yes.
So because the difference is co-continuous, it means there's just a single profunctor that represents the whole difference calculus. So I think that's kind of neat.
Uh-huh. Yes. Yeah.
Thank you.
Thank you. Yes.
So, more questions or comments? So, if not, let's thank the speaker again.